Hello, welcome to this video where I will show you how to use a MOSFET to drive a motor and the additional circuit components that you may need. And I'm using an Arduino to drive the circuit. I'm going to give you a short demo before we begin. As you can see, the motor is controlled by the Arduino with the flash of this light. It's a small program. Okay, I'm going to explain what's happening over here, and for this circuit I'm going to be tracing the flow of electrons. Okay, so this is the negative side of the battery, so we will start here. So the negative side has this white wire that comes up to this orange wire that comes up to this this negative rail. Okay, so there are two more things connected to this negative rail. Let's trace them. So this purple wire comes out to a ground pin on the Arduino. Okay, so this negative of the Arduino power supply and the battery, the two negatives are connected as a ground. My Arduino is powered from my laptop right there. Okay, now what else? So there is another orange wire connected to this negative rail. Excuse me. So this negative wire comes up to the rightmost pin of the MOSFET. Let me try to focus this. So here is the MOSFET, and that orange wire comes out to the negative pin, the rightmost pin of the MOSFET. So let me draw this out, what we have so far. Okay, so we have a cell, the battery, it has about 9 volts. That's our negative rail. Here is the connection to the Arduino ground. I'm labeling that A for Arduino. Arduino has its own power supply, by the way, from the computer, but the grounds should be connected. Now this is the source pin of the MOSFET. Okay, I'm going to take some liberties here and draw out the MOSFET in a little unconventional way, because that to keep the alignment with this as true as possible. So the leftmost pin over here is the gate of the MOSFET. The middle pin is the drain of the MOSFET. The last pin is the source of the MOSFET. Okay, so we have the source connected to our negative rail, and then here is the drain pin, so it's the middle pin. I'm gonna pass it through, just pretend you didn't see that. So that's the drain in the middle, and here is the ground. So I have, no, sorry, it's called the gate. My apologies. Gate, drain, source, just like it's here, gate, drain, source. Okay, I'm gonna put a circle around it. Before we move forward, I just want to point out in the MOSFET, the way this works, this is an electronic switch. So if there is a potential difference between the ground and the source, this switch is on, and electrons can flow into the source and out the drain. Okay, so electrons can flow through here. But you need, for that to happen, you need a potential difference between these 2 points. Okay, between the gate and the source, there has to be a potential difference. If there is none, this is off, nothing's gonna happen. Okay, now we know where the source is connected. Let's look at where these go. For now, the ground pin is yellow and it's not connected to anywhere, it's just floating here. And then the middle pin, the drain, it's a red wire. It comes up to over here. What's over here? Excuse me. Over here I have a rail with 3 components connected. I have a red wire going out, I have a capacitor, and I have a diode as well. Let me try to focus so that you can actually see the diode. Okay, so to this negative rail one leg of the capacitor goes, one leg of the diode goes. Now, as you may have noticed, the negative side of the diode, the band of the diode, is facing the other way, so electrons cannot pass through the diode. Okay, so I'm going to draw that over here. To this is connected a capacitor and a diode in reverse mode, so it's pointing away from the, like, it's pointing this way, but electrons must come through this way for it to pass. So if you want electrons to pass this way, it cannot pass. Also connected to this is another red wire. The red wire comes up to this motor, okay, and then the motor goes on through this black wire to this black wire to connect to the battery, positive side, and there's another brown wire. Okay, so let's draw the motor. I'm going to use an inductor symbol for the motor and then connect that to our battery. I'm gonna do an M for a motor, and let's follow the brown wire now. That's also connected to the positive. That brown wire goes back here and connects to the cathode, the side with the band of the diode, and the other leg of the capacitor. So capacitor, go there, diode, you go there. So as you can see, the motor, the capacitor, and the diode are in parallel. Now let's explain why these are here. Now the capacitor is used to smooth out the noise produced by the motor. Here is a simplified diagram of the commutator that connects the two coils of wire. There are many splits in a commutator, but to simplify, I have just drawn two. Now this is always the positive from the motor, this is always the negative, or it could be flipped, but it's fixed, right? So when the motor goes around, the coils need to be switching their currents to continue rotating. So but at the gaps, the coils cannot draw current, so they draw some current when the commutator rotates and the brushes are connected to the commutator body. There is a flow of current, but when in the middle they're not connected to anything, current does not flow, and that produces some electrical noise. The capacitor helps to smooth that out by storing charges and releasing them when necessary. What's more interesting to me is this diode. This is called a flyback diode, and we can talk about how that works. Okay, so we're gonna get back to the MOSFET in a minute. So imagine the MOSFET, there is some potential difference here between the gate and the source, and the MOSFET allows current to flow. So current, so again, when I say current, I am saying the flow of electrons. So electrons flow from here, through the source, through the drain, through the motor, out here, through here, back to the positive, right? No current flows through the diode because it's reversed, and current cannot actually flow through capacitors. They can react to sudden changes, right? Or they can be charged up and whatever. Now what's interesting is if it's on, that's fine, but when we turn that off, something interesting happens. So the motor is a coil of wire and it's an inductor. Okay, the motor is connected, is an inductor. What it means is that it builds up it builds up magnetic fields around its coils when it's operating. Okay, and it stores some energy in the fields, and when the switch closes, so no more electrons are coming, it's closed suddenly, the field collapses, and that tries to keep the electrons moving. Simpler analogy for us, I have a mechanical analogy. So here is here are two springs, okay? So this represents the flow of electrons, okay? Imagine this is the switch that will halt the flow of electrons suddenly, and this is the motor that wants to keep going. So electrons keep flowing, and when the switch suddenly stops the flow of electrons, the motor, because of its electrical inertia, will try to pull everything away. And now this is a voltage, right? So you are trying to pull more current. Now if this switch is weak, the switch may break, because again, notice that in this MOSFET there are no mechanical connections, right? So if you apply enough voltage to try to rip electrons away from it, the electrical properties of this MOSFET may break down, and anything else connected to the motor on this side or that side may be affected, right? So this is not good for sensitive electronic components. So we can think of this as, normally when the motor is operating, it takes in electrons to that side, so that side can be considered positive. Electrons exit from that side, that can be considered negative, okay? But in reality, you know, they don't have, this does not have any force to it, except when this suddenly turns off. Now this side really becomes positive because it wants to, now again, this is momentary, this wants to keep the electrons going, so this becomes really positive, this side becomes really negative because it wants to pull the electrons across. Now if this diode was not there, this might be damaged and other components might be damaged, but because this flyback diode is here, notice what happens. So I said this side is negative, right? Electrons wants to continue from here. However, the diode provides an easy path for the electrons to actually simply circulate here. How? The electrons come through here. Now, because this is reverse bias, the electrons can enter from this side, right? Because electrons can always enter the cathode side of the diode, so electrons can enter through here, come back to the motor. So whatever angry reaction the motor gives us, that angry reaction will be contained within this circle, okay? Electrons can flow, keep flowing until the motor comes down, or the inductance. So there is no sudden impact on the on this or anything. You can also think of this as like there is a lot of water flowing, there is a water wheel moving the water along. It has a lot of inertia. When you suddenly cut the tap, you know, the wheel will still want to keep moving and push the water along, and that may damage your valve over here. But if you give it another path to circulate the water, it will simply circulate the water until the wheel loses its inertia. That's why the flyback diode is needed. In my case, I'm using a Schottky diode, so these are diodes that have relatively low activation forward voltage, so it's 0.2 volt compared to regular diodes, which is about 0.7 volts, so the current has an easy path to travel. So I explained these two, so that's the motor part. Let's talk about this, okay? Okay. So in the MOSFET, this is the gate, and there is a source connected to the negative terminal of the battery. Now, I did not talk about this resistor, okay? So let me take this resistor off and show you what happens if I don't have this resistor. By the way, the resistor connects the gate and the source, and this is a high resistor, 10 kilo ohms, okay? So here's the motor. Watch what happens if I touch this. The static electricity from my body is enough to cause a potential difference between the gate and the source, and the motor should start running. Okay, so I touch that, and let me touch this so that there is some potential difference between these 2 points. Let's see. You see the motor turning on because I touched this. Oh, it's now angry. It's just turned on. I am not touching anything anymore. It's just turned on. So what happens is that this is in a half on state because there is some charge from my body because I touched stuff around. There is some static electricity in my body that just stays there. Because there is nothing connecting the gate and the source of the MOSFET, it will allow current to flow from the source to the drain and drive the motor, right? Okay, that's very weird. It works sometimes, it sometimes doesn't work. Okay, let me turn it on again with my static electricity. Okay, it's turned on. Now watch what happens when I connect the source and the drain using this resistor, so that there is no more potential difference between them. The electrons can equalize between them. So okay, once I've connected that, now no matter what I do, the static electricity from my body is not enough to turn it on, because any small charges over here will just go through the resistor and balance these out. Okay. Okay, let's go back to our diagram again. So when these are not connected, when I touch this is my finger, there is an electron, that electron just sits here, and there is some potential difference between these two. For if I'm positively charged, it will take away electrons from me, and then there is some potential difference between these two, and it stays on, right? And then current can flow to the motor. Now in my circuit I have a resistor over here, it's 10 kilo ohm. So this is a pretty high resistance, and through here when I touch this, any stray charges will just pass through. Now what I can do is connect my digital output pin. In my case it's pin 13. I'm turning that to high, so that there is so this is a positive voltage on the ground side, okay, and the source is connected to the negative side of the Arduino and to the battery as well, but since this is the Arduino circuit, it will flow through the Arduino. So let's follow that. So some current flows through here, okay. This is the circuit through the Arduino. The Arduino supplies 5 volt, so the voltage drop across this resistor is 5 volts, so that's important. So there is a voltage drop across a load. So the only load I'm imagining over here, the resistance of the wires being negligible, is this 10 kilo ohm resistor, and across this resistor is 5 volt. Now that 5 volt applies between the ground and the source, because to one leg of this resistor is the source, in another leg of the resistor is the gate. Did I say ground again? This is the gate. So the difference between the source and the gate is 5 volt, the voltage supplied by the Arduino, and then this moves forward, okay. In my Arduino code I have heartbeat type thingy. I'm not going to show you the code, but I'm going to show you the LED. The LED just blinks as if there is a heartbeat. So I think this is better and out of focus. Now that blinking is on pin 13, and I'm going to connect the gate that was floating all this time to pin 13, and notice what happens to the motor. Okay, so here is pin 13, I connected. So with the LED, the motor turns on and off. That concludes my demonstration of how to run a motor, anything that's of a higher voltage, using a MOSFET and a low voltage signal, 5 volt signal from an Arduino. This motor is running on 9 volt. You could have used a 12 volt circuit or larger, though I wouldn't recommend it for safety reasons.